Today we're happy to have Andrew Liddle all the way from Lisbon to tell us about DESI.
Indeed. Thank you very much. Let's see if I can get the screen sharing working correctly. Okay, let's go. So I'm going to talk about two separate papers, which are both written with Marina, who you just met. One of them, DESI, I'll keep for part two, because that's the super topical part of the story. And the first one is going to be work on cosmological tensions. And the common theme that unites these is searches or signatures of new cosmological physics coming from astronomical data of various kinds. Now, first of all, I'd just like to say I'd like you to interrupt me as much as possible, especially because I'm aware that I'm a kind of astronomer, cosmologist, and we love our jargon. And not all of you are, I think, cosmologists or people who might have heard a lot about cosmology. So if I lapse into jargon or things aren't making much sense, I really want you to shout at me and get me to explain some of the things that I'm talking about. I'm not going to spend much time on general introduction because I think this is pretty well-known stuff. We've had a cosmological model which has lasted now for around 20 years or so, which is an extraordinarily successful model based on 6 parameters. Exactly what you say these 6 parameters are depends on which parameterization you're choosing, but more or less these are the quantities of different kinds of material in the universe, the baryonic matter, the dark energy, and they are properties of the perturbations in the universe that give rise to structure formation, cosmic microwave background anisotropies, etc. And that latter, the perturbations, are normally parameterized by 2 parameters, an amplitude and a slope. And the way we think this is a good model is that we have data from, say, the Planck satellite cosmic microwave background anisotropy measures, which are by far the strongest, shown on the left here. And the 6-parameter model fits data like this extraordinarily well. The error bars are on the red dots are too small to see across a very wide range of scales. This is showing the temperature, but there's also polarization anisotropy, very accurately measured. And then there's a host of other kinds of observations, like the clustering of galaxies. And if you start with the 6-parameter cosmological model, we normally call LambdaCDM, observations like these will determine all 6 of the parameters extremely well. And so it doesn't really matter what the parameters are, but you can see in the little table on the right-hand side that all of these 6 parameters are measured, and the error bars are in some cases extremely small, and in all cases are quite constraining on the parameters that are under discussion. So this model was established in the late 1990s, more or less, is when lambda became unarguably part of the standard cosmological model. The basic parameterization was fixed by WMAP around 2003 with their first measurements of the cosmic microwave background. And then the 20 years or so since then have all been spent pretty much refining the values of these different parameters, with Planck satellite combined with various other data giving the state of the art for the 6-parameter LambdaCDM model. Now, if you've been facing a model like LambdaCDM for 2 decades, then you're going to be getting pretty bored with it by now. And I think that's especially true for cosmologists because we're not actually very good at understanding what these 6 parameters are that we've measured. As I'm sure you're aware, we don't really know what the dark energy or the lambda might be, even though it's measured quite accurately. We can't even predict the baryon density from first principles, far less the cold dark matter density, etc. So on this side, theoretical understanding of this phenomenological model is not very good. We haven't progressed to a fundamental understanding of the 6-parameter model, but also we're pretty desperate to get past that model as well and find something new. And this is the recurrent theme in most of the cosmology work that you're seeing. So I'm going to talk about 2 different pieces of evidence which have been much invoked as possibly suggesting that the LambdaCDM cosmological model, the 6-parameter model, is not adequate. Now, one of these has been around for a decade or so, so I expect everyone's at least heard of it, if not in detail, and you have in Lloyd Knox, someone who's worked a lot on this over the years. The Hubble tension is a discrepancy between different observational measurements of the expansion rate of the universe, and I'll describe in a little bit more detail. It's been around for a decade or so. It's been oscillating around, but generally increasing in significance until recently, and is commonly said to be at something like the 5 sigma level, which has been captured by cosmologists from particle physicists as being the point at which you might hope that something was unarguable. Though, as you will find from my talk, I think the Hubble tension is far from unarguable, whether it's 5 sigma or not. That's about a decade old. The other thing, which is I think why I was actually invited to talk, is the recent announcement of results from the Dark Energy Spectroscopic Instrument collaboration about 1 month ago, just a little bit more than 1 month ago, where they made what they call a tantalising suggestion that the dark energy density is evolving. Unlike in the LambdaCDM model, where the dark energy density as a lambda is a constant throughout all of cosmic history. And what we'll see when we look at that is that this result, depending how you analyze this, claims to be at something like the 3 to 4 sigma level. So these are the two things. I'm just going to do one after the other and possibly spend actually a little bit more time on data set tensions, because there's a little bit more detail to talk about in that. But we'll see. So Marina and I have a paper on this that we put out late last year. It's published now in monthly notices. And we actually didn't publish it for a very long time. The basic calculations we did when we were visiting Perimeter Institute in 2019. And I always thought, oh, the Hubble tension was our main motivation. And I thought, oh, it's just going to go away. It's not going to be around for very long. And it took us a while to build up the energy and enthusiasm to put the paper out and discuss it. Very much inspired by a visit that Marina made to California, and particularly to the Lawrence Berkeley lab in July last year, where she talked to some of the researchers there, and they definitely gave us a strong push to put our paper out and discuss our viewpoint. So data set tensions. If you hang around with cosmologists for any length of time, you will hear the word tension mentioned a lot, particularly the Hubble tension. You'll see it on the archive. If you look at the papers, you'll hear it in conferences. You probably hear people muttering about it in your corridor all the time. People talk about tensions amongst data sets as being one of the important aspects of current cosmology. And mostly I'm going to focus on the Hubble tension, but there are other perhaps less significant tensions that are mentioned from time to time, particularly a so-called sigma 8 tension about the amplitude of density perturbations in the universe, which at one time seemed to be 2 to 3 sigma, but more recently has fallen to well below 2 sigma, and I feel is not really worth much attention. So the Hubble tension for orientation is shown, a sort of summary of some measures of the Hubble constant are shown in this figure here. Ofer Lahav and I write the cosmological parameters review for the Review of Particle Physics. It comes out every 2 years, so we update our version of constraints. This is a very small summary of what we think are the most important constraints on the Hubble constants. Review articles on this topic can have tens or more of data points shown. But really the only important ones anyway are 2 of them, which is the Planck measurement at the top and the Shoes measurement in the middle. And the Planck measurement gives the Hubble constant at 67.4 plus or minus 0.05. Shoes is 73 plus or minus 1. And the discrepancy between these 2 is about 5 sigma. So before getting into that, in the other measurements you can see are broadly consistent with Planck, and some of them are also consistent with Shoes. So the main tension here is between Shoes and Planck. Now, these are very different kinds of observations and with very different ambitions, and it's first important to make that clear. So Planck measures all the parameters of the standard cosmological model, the 6 parameters, measures them all to quite high precision. And from that, you can infer any property you like of the cosmological model. And in particular, you can infer what the present expansion rate of the universe is. You're not measuring it directly, but you're learning from how physics work, mostly to redshift of 1,000, how the basic cosmological models put together. And then you predict, run it forward. And because the cosmological model is fixed with such exquisite accuracy by the cosmic microwave background, the prediction for the present day Hubble constant has a very small uncertainty, just 0.05. SHOES is a project which is primarily using Hubble Space Telescope data, now transitioning to James Webb, led by Adam Rees, who already won a Nobel Prize for his work with in discovering the dark energy in 1998. And this is a direct measurement technique. This is the real attempt to figure out what is the distance and recession velocity of a bunch of objects. Ultimately, these are supernovae at some moderate distance away from us, but there's a distance ladder of calibration to try and understand how far away distant objects are, which starts in the neighboring universe by looking at the properties of Cepheid variable stars. And by very long, detailed sets of observations, they've been working on this. Well, this technique's 30 years or more old. SHOES has been going for over a decade, I think. They've refined their measurements of systematics and other things and believe they can measure the Hubble parameter to be 73 plus or minus 1. And this measurement's only purpose is to measure the Hubble parameter. It doesn't tell you anything about any other piece of cosmology. So these are the two observations. They are 5 sigma apart, and 5 sigma is a lot. So you clearly want to look at this data and try and figure out what you might learn from it. So why might data sets be in tension? Well, there's a whole bunch of reasons, and we want to think carefully which ones might be the relevant ones. So here are 4 good reasons why you might discover that 2 different ways of measuring something are in disagreement with each other. For relatively small variations, statistical fluke is perfectly possible. And I would say, anything less than 2 sigma, statistical fluke is perfectly reasonable. Above that, it depends how many measurements you might have made, whether that's reasonable or not. But for small amounts of tension, statistical fluke is the most likely thing, especially because people draw attention to results that happen to be a little bit discrepant from standard understanding while not mentioning ones that are not. Second possibility is underreported systematic uncertainties. In this regard, astronomy is trickier than particle physics, I think, because you're not really under control of the thing you're observing. You're just looking at something that's out there, and you don't necessarily know exactly what kind of uncertainties might be being accumulated. A good example of that was about a decade ago. People thought they had measured so-called B-mode microwave background anisotropies, the BICEP experiment. It turned out that instead there was a systematic uncertainty of emission from dust in the microwave part of the spectrum, which turned out to be much more important than primordial signal and completely dominated it. And so their neglect of that systematic meant that they'd drawn the wrong conclusions initially from their data. So this is certainly a possibility, and almost all the work in any large cosmological survey is on trying to figure out and minimize and model systematic uncertainties of various kinds. The third thing, not often talked about, but I like to mention it, is data analysis pipeline errors. Modern surveys have hundreds of people working on them. DESI is a good example of that. SHOES is a bit smaller. The codes are incredibly complicated and lengthy, and everyone knows in their heart of hearts that it's impossible to make very large, complicated codes written by very many people absolutely guaranteed to be free of errors. I know this from firsthand experience. I work in a survey called the Dark Energy Survey, DES, as it's called normally in the US, which is a kind of precursor to DESI in many ways and has lots of the same people. And during the analysis process and after publication of results in one case, we uncovered quite significant pipeline errors which had to be corrected. Now, you can try and mitigate this by having multiple independent chains. The Planck satellite, for example, almost all of the main analysis has got 2 completely independent pipelines leading to it, but ultimately you're limited a little bit, and so it's always a possibility. But the fourth one is the one that gets physicists interested and theorists interested, which is that the data sets might be in tension, not because there's something wrong with the observations, but because there's something wrong with the model, that the cosmological model we're dealing with to try and explain the observations is inadequate in some way. So this is the modern trend. Data set tensions are frequently invoked as signaling new physics. And the phrase people like to use, especially in the abstracts of papers, is alleviating the tension. So you'll see someone saying, oh, I've got this fantastic modified gravity model that I'm going to use, and it will alleviate the tension, Hubble tension, so that it's only 3 sigma instead of 5 sigma. So it turns out there are an enormous number of models. I've deliberately made these really small so you can't read them properly at all. But just to give you a flavor, these are 2 review articles, both a couple of years old, listing an endless set of different possible models that have been proposed to try and explain the Hubble tension. So the idea here, if you look at the left one, is that the blue is where the shoes is, the red is where Planck would be given the LambdaCDM model. But if you change your cosmological model, you change the inferences that you would get from Planck, and you can change the prediction you would have for the present day Hubble parameter. So your goal in these models is to shift the predicted value of the Hubble parameter from the Planck value towards the shoes value. And models succeed by varying amounts in trying to do that. Often incurring, however, significant other kinds of observational difficulties in the process. Now, I'm going to spend a little bit of time talking about Bayesian methods in the analysis of tension, because I like Bayesian stuff a lot, and so I like to have a chance to talk about it. Some of it will be a little bit detailed, but we'll get through it in 5 or 10 minutes, and then we'll get back to the more regulation stuff. But I think it's useful to see some of these formulae and get a picture for how Bayesian analysis works, because most cosmology is done within this framework. And when it comes to tension, there's a variety of different methods in use. There's fully Bayesian methods, which I'm going to describe here. There's partially Bayesian or almost entirely frequentist methods, but they all more or less have the same characteristics, and what we'll see is the same shortcomings at the end. So we're talking about tension between data. So there's going to be 2 different data sets that are going to be exhibiting the tension. So these are going to be called A and B throughout. And then there's the model being assumed, which I'm going to label with numbers 1 and 2. And the standard way of defining the tension within a model, so here I'm just assuming model 1 is correct, goes back to a paper by Marshall et al. In 2004. And this is just to get you used to this terminology if you've not seen the Bayesian kind of formulas before, that they're all probabilities, and the vertical line is given such and such an assumption. So here on the numerator, I've got my 2 data sets, data set A and B, and I'm considering both of them. I'm going to assume the model. In this case, I've only got 1 model, so model 1 is the one being assumed. And the numerator says, what is the probability of the data that I've got, both data sets A and B, given model 1? And then on the denominator, there's something that looks at first a little bit odd. It had me scratching my head for a while, which is you take the product of the probability of the data of data set A given model 1 and the probability of data set B given model 1. And there's words that go along with this, which is to say that on the numerator, you're requiring that both data sets are fit with the same values of the parameters. Let's say it's the 6-parameter LambdaCDM model. So you have to fit all of the data, and you're only allowed to vary the parameter. The parameters have to have the same value for each data set. On the denominator, you're allowing the different data sets to be fit with different values of the parameters. It's as if the 2 data sets live in different universes, if you like, where the parameters, the Hubble parameter or the baryon density could be different. And you take that product. Now, clearly, the notion of tension or agreement between the data sets is something to do with the data predicting roughly the same parameters from each of the data sets. So it looks sort of reasonable in a way, but I don't find it's very easy to understand. And I think there's a much better way to express the same thing using Bayes' theorem, which just lets you shift around the probabilities a little bit. So this is the same thing, but now on the numerator, we have the probability of data set A given data set B and the model assumption. And on the denominator, we just have the probability of data set A given the model assumption with no reference at all to data set B. So the words that go with this is that on the top, you're going to, your knowledge is both your model and the existence of data set B, whatever you can learn from data set B, and it asks, how good does data set A look like? Whereas on the denominator, it's just how does data set A look on its own? So if you have data set B in hand, does that make data set A more or less likely? That's the question that's being asked. Does data set B support data set A, or does it oppose it? And the two data sets could be inverted. You could have the B first and the A second. It would be the same formula. And this, I think, is a much easier way to understand it. It's asking whether the two data sets are reinforcing each other or opposing each other. And so this tension ratio has become quite a popular measure to use. And you get similar things from other definitions, but I like this one because it's a fully Bayesian one. So what do you do with this tension metric? Well, what Marshall et al. Had in mind, and what we used in the dark energy survey quite a bit, is that the tension metric is supposed to test whether or not the two data sets are consistent or not. That's its definition. So I want to know, are my inferences from data set A and data set B consistent with each other or not? And the idea was that if they're consistent, you could then combine them and carry out a joint analysis. If they're not consistent, then you shouldn't combine the data because you're thinking there must be a problem with one of the data sets. And so in dark energy survey, we had thresholds that the tension metric had to satisfy in order for us to be allowed to combine data sets of different kinds, like galaxy clustering in the cosmic microwave background or gravitational lensing. So that was what everyone had in mind. But at some point in the last decade or so, the tension metric has suddenly started meaning a different thing. And it's worth paying attention to this change because it's almost like a bit of a magician's sleight of hand. You've been asked to look one way. You thought you were used to the idea of what this tension metric is. But suddenly it's taken on a different meaning, which comes from the fact that the amount of tension depends on the model which is under consideration. It's very important to always have this in mind, that tension between data sets is not just a property of the data sets alone. It's a property of the model that you're using to fit the data sets. And you might find that if you'd chosen a better model, the tension would have gone away. That's the principle of new physics coming from tensions. So suddenly the tension metric's being used for this purpose. Reduce the tension, then you're favoring, say, model 2. And normally this would mean some extended model with new physics taken into account, parameterized by some number of new parameters, might be evolving dark energy, might be self-interacting dark matter, who knows, and anything you like really, but some extra ingredient over the LambdaCDM. Now the sort of switch that's happened here is that the tension metric used to be used to test whether or not the data sets were consistent with each other. And that's because people suspected that they might not be, and that could be a signature of systematic uncertainties not being fully accounted for. Suddenly, instead, in this model testing, we're going to assume the data sets are perfectly good and that all of the blame for the tension is suddenly on the model rather than the data. Now, in reality, clearly the truth's probably at best somewhere in between the two. But it's a very significant step when you're using the tension metric to suddenly be believing that the data sets are in some way perfectly represented by their quoted error bars. But if that happens, then people will say that the new physics is motivated by the reduced tension. Now, the thing I want to discuss is whether or not this is actually reasonable or true. And to decide that, you have to use the correct Bayesian quantity for deciding whether one model is better than another is the ratio of model probabilities. So here we have the probability of model 1 given all of the data, so both data sets together, and we have the probability of model 2 given all of the data. And the ratio of these probabilities tells you which model is better. And this is the unique correct Bayesian quantity for deciding whether one model is good or not. You can calculate it in using, again, a version of Bayes' theorem. The model probabilities are not directly predicted. What you can calculate is the probability of your data given the model, which is this thing called the Bayes factor down at the bottom. I won't go into how that's calculated. It can be quite a complicated and arduous computation. But the gist of it is that by calculating how probable the two data sets together are given your model, you can use that to update a prior model probability, the ratio of M1 and M2 on the right-hand side, to get the model probability given the data. And you can calculate it in various ways. The prior model probabilities are up to you to choose. That's where you can be a theorist and decide which things you like and which things you don't like. But everyone should agree on this Bayes factor that tells you how the model probabilities have been changed by your calculation. So when someone comes along to you and says, I'm going to use the tension ratio to diagnose new physics, they're saying that the tension ratio is basically the same thing as the model probability ratio. And this was a calculation we did way back in 2019 and never got around to publishing for ages. And it's almost just a one-liner. You have the tension ratio written there. You have the Bayes factor, which is the thing you actually want to use. And you can get a formula that relates the two of them that says that the Bayes factor, the model probability change, is given by the ratio of these tensions, but also multiplied by other factors as well, which are the probabilities of the separate data sets A and B. And I can use their Bayes factor if I want to write this in a condensed way like this to say that the model probability when I combine two data sets is given by the product of the model probabilities of data sets A and B, but also corrected by this tension term. And that's quite a nice formula. If you're used to Bayesian updating, you might have expected that there wouldn't be a tension term here and you just update the data by multiplying the Bayes factors together. But that's not true. The amount of inconsistency or consistency between the data sets also features, and this tension ratio is actually exactly the quantity that quantifies that. So this puts us in a position, first of all, to say that tension factor and the Bayes factor are not the same, so the tension ratio cannot be the whole story, but it also shows you how to break down the probabilities into the different parts. So if you want model 2 to be favored, there's 3 different ways it can happen, depending which of these terms on the right-hand side is the one which is bigger than 1. It might be better just because it fits data set A better, or it might fit data set B better, or it might reduce the tension between the data sets. And these are the 3 possibilities for why model 2 might be favored on theoretical grounds. So the tension ratio is not the whole story at all. And in particular, if someone comes up to you and says reducing tension is going to motivate my new model, and really almost every paper in the cosmology literature does exactly that. You read the abstracts and they all say, oh, I've got a new model and it's reduced the tension from 5 sigma to 3 sigma. This is not the whole story at all. It's not they're not giving you the correct calculation. The Bayes factor is the correct calculation. Any reduction of tension is only indicative because it's quite likely that those models will fit the data, the individual data sets, much less well, because any extra parameters are reducing the predictiveness of the models. And we already know that LambdaCDM fits the data sets really very well. So there's very little room to improve the fit to the data by introducing new parameters.
Sorry,
so
this
all of
like,
that was the maths to motivate.
Question?
Yep, please go ahead.
Sorry to stop you, but this seems like maybe an important point. And the formulas are simple enough. I can't complain about any of the formulas, but it sounds like you have a more intuitive understanding of this point. I always find it useful to sort of be able to think about statistics and questions in a more intuitive way. So if you had, can you give me maybe an example where suppose you model 1 significantly reduced the tension?
Yeah.
Okay.
Well, yeah. And yet, I think I may be answering some of this on the next slide. Maybe you're going to do that. Okay. Let me see. Ask again once we get through this slide and see whether or not it gives you.
Yeah.
So, so a few points related to this, which are still maybe a little bit abstract, is that if new physics is going to show up via the tension, this actually requires quite a coincidence. This would be true for any topic, but particularly I'm thinking of the Hubble tension here. Because what it means is that the wrong model, which would be LambdaCDM here, has to fit the 2 data sets separately every bit as well as the right model does. And yet it has to fail badly when these 2 data sets are combined together. Now, this would be a big surprise for Planck data in particular, because the Planck data is unbelievably strong and also is not directly measuring the Hubble parameter. It's an inferred parameter, which is emerging as some complicated combination of the constraints on the base parameters. Now, I was actually surprised to discover just how constraining Planck is. It's a 6-dimensional parameter space, which is quite big, but the Planck data reduces the prior volume by a factor of 2 × 10⁻14.
How's that prior?
100 in every parameter direction. So the data set is extraordinarily constraining, and which is, I should say, a bit unlike the case with the Hubble.
Andrew, I think we have a question.
I just
Go
wonder
ahead.
about how that, I'm intrigued by this 2 times 10 to the 14, and I'm wondering how the prior is defined here.
Well, I'm literally taking the Planck priors. So the Planck priors stated in their paper are fairly broad. They're probably not as broad as people might have thought they could have been back in 1990 before any measurements were made. But they're pretty broad, and that's partly gives this big factor. The dark energy survey.
Okay.
Dark energy survey uses much narrower priors, but still gets about 10 to the 7, I think, reduction from prior to posterior. That's about a factor of 10 in each dimension.
So it's some fairly arbitrarily set cubic volume of parameter space.
Yeah, that's right. And the Planck prior was really trying to represent a time when we knew nothing about cosmological parameters. So the fact that they're now all measured to percent level is basically just saying we've gone from knowing nothing to knowing everything to percent level. And that in 6 dimensions gives more or less the number which I've specified. It's a very different regime from the Hubble constant measurements, where the prior range was maybe from 50 to 100, and it's constrained by a factor of around 20 or so only. So the Hubble constant data, in a way, no theory tries to predict the Hubble constant from first principles. So every model you ever come across can always fit the shoes data perfectly by just adjusting the Hubble constant to be the observed value. It's only when you combine it with Planck that you get this discrepancy between the values. I guess I'm not sure whether I really did answer the question about definite examples there. Maybe I'll say it again in the conclusions and then see if that answered it. So my first point would be that any analysis that claims new physics based only on alleviating tensions is an incomplete analysis, just on statistical grounds. And a particular misunderstanding people seem to have and be willing to propagate is the idea that if you reduce the tension, say, by 2 sigma, that might justify a physics model with 2 new parameters, because they're thinking, oh, there's some kind of chi-squared per degree of freedom thing going on here, so my improvement of fit is worth 2 parameters. But that's statistically makes no sense, because sigmas of tension are not related to sigmas of data model fit. So you can't use that argument at all. So anyone who says just uses data tensions to justify new parameters, you should look at them with some level of suspicion. But the second point I'm trying to make, I think, is mostly true about the Hubble tension specifically, is that because of this big imbalance between the strength of Planck and the strength of the Hubble data, if you were to ever produce a new physics model that could explain the tension, you're immediately faced with a new massive and troubling coincidence as to what hid the true model so well from the separate experiments, particularly Planck, in a way that only let it be revealed via the tension with this other not very constraining data from the Hubble parameter. And the trouble is, all the new physics models in that table I showed you earlier, they have new parameters, and those new parameters could take any values you like, as far as we know. And you have to tune them with extreme care to make that new physics model look like LambdaCDM to Planck, and yet have it not look like LambdaCDM in a way that can create a Hubble tension. So it's like a whole new level of coincidence. And because of that, Marina and I came to the view that new physics explanations are much harder than the community at large seems to believe, and we're rather skeptical about the large numbers of papers emerging claiming these different kinds. And so because of that, we would infer that unidentified systematic uncertainties in the observations are a more likely source of the tension than new physics as compared to the community view at large. So that's where it kind of rested, and we submitted our paper, and it's now published. But I did want to end this phase of my talk with a brief stop press, which is that about 2 or 3 weeks ago, there was a meeting at the Royal Society in London where Wendy Friedman gave a talk of showing preliminary results from the Chicago Carnegie Hubble project. This is essentially the main rival to the SHOES project there. And she shows some preliminary results, which are still not published, I believe, but this is a snapshot of her slide. You can see her on the right giving the talk with John Ellis chairing in a rather splendid jumper. And she, I think it's Maxwell's equations, I think, something like that on it. But she dropped a bit of a bombshell, which is that she has JWST measurements of the distance ladder, including Cepheids and also different calibrations using the tip of the red giant branch and the so-called J region asymptotic giant branch. These are 3 different methods of trying to calibrate the local distance ladder before you extend out to look at the supernova distances. And what you can see at the bottom is that her result is 6, and her team's result is 69.1 plus or minus 1.5, is really quite different from the SHOES result. And in the plot, you see SHOES is over on the right, Planck is the spiky one on the left. And their new measurements, which are the competitor to SHOES, are much, much closer to Planck. And if you squint very carefully, you can also see the 3 separate calibrations they have. I think their Cepheid one, which is the most directly comparable result to SHOES, is the dark blue, so it's a little bit more towards SHOES. But this is not yet published, so who knows for sure whether it's going to change or not. But this is new data. It's James Webb Space Telescope, so it's superior to the Hubble Space Telescope data. The SHOES collaboration are also working with James Webb data, of course, and so the story is going to be open. But to me, this is certainly could be a first sign that the Hubble tension is going to fade away in some way and turn out not to have actually been due to new physics after all.
Sorry, can I ask a question?
Yeah, please. Yeah, I don't have too many questions now because I want to talk about DESI, but I think a couple of questions at this pause might be good.
Okay, I'll ask afterwards. Why don't you go ahead and finish your talk? Maybe if you can stay afterwards so we don't delay your talk.
Yeah, I mean, if people want to stay, yeah, I can chat for a while afterwards then, but I'm sort of aware I've spent maybe 5 minutes longer than I intended to on the Hubble tension. I don't want to run out of stuff on DESI. So DESI is new. Marina and I had a look at it and we thought, oh, we have an opportunity to write something rather quick, just making a few points about it. And so we did that and we wrote a paper in about a week after the data came out. There were many, many papers coming out and roughly they appear at 1 a day. And the reason is because DESI has come along and given what they say is interesting evidence for the possibility that the dark energy density is evolving with redshift. So DESI, Dark Energy Spectroscopic Instrument, is led by DOE, particularly from the Berkeley lab just down the road from where you are. It's the first survey of so-called stage 4 type. And they do various different kinds of measurements, but the one which has been released now, which has been getting the attention, is the so-called baryon acoustic oscillation observations. And this is a measurement of a feature in the galaxy power spectrum, which is the analog of the peaks in the cosmic microwave background. I'd like to have more time to explain it, but essentially it's a peak in the galaxy power spectrum, which is at a scale which can be very accurately predicted as a function of redshift and can be measured at a series of redshifts by looking at different kinds of galaxies. And DESI made 7 measurements going from a redshift of about 0.5 out to 2.5, I think. And it's a major, major survey carried out really to a very high standard. Hundreds of people have been working. There's multiple, they use blind, 800, Marina tells me. They use blinding techniques to make sure they don't know the results ahead of them coming out, the independent pipelines. It's a fantastic experiment. The things that we're going to say are all entirely on the very theoretical interpretational end of it, but we love the DESI experiment. We think that it's a very fantastic experiment. Now, main results we'll be showing don't come from DESI alone. You have to combine it with other data in order to get something interesting. And in particular, we're going to be combining it with the Planck cosmic microwave background anisotropy data and also microwave background lensing data, which uses, I think, must be Atacama Cosmology Telescope data along with Planck. And also particularly supernova data, this classic luminosity redshift data that was used first to discover dark energy. And you mix these three data sets together and their headline claim is they have found tantalizing suggestions of evolving dark energy. Tantalizing suggestions you can interpret in different ways, but it clearly means they're making a claim of quite a strong result, but falling short of really saying this is definitely true and we're going to bet our future careers on it. It's somewhere in between, as you'll see. I'm going to just orient us by saying what is the model we're dealing with. Their paper discusses a couple of things, but all of the interest is in a single phenomenological model of dark energy, which has a two-parameter equation of state called W0 WA. I'm assuming probably most of your audience is familiar, but just in case not, I wrote down the details here. So the idea is that we have the scale factor of the universe running from 0 at the Big Bang up to 1 at present. And the dark energy has an equation of state, which is the ratio of pressure to energy density, which evolves with scale factor or equivalently with redshift. Its initial value at A equals 0 is W0 plus WA. And by the present day, it's evolved to be equal to W0. So, and it's a linear extrapolation. So it's a very simple model introduced first by Chevalier and Pilarski, and later also studied by Eric Linder, and particularly popularized by the Dark Energy Task Force, which your own Andy Albrecht was a major player in 2006. So this is the model. Contains cosmological constant as a special case. The cosmological constant has equation of state -1 at all times. So W0 equal to -1 and WA equal to 0. And also very important for this discussion is that these models can have what's called a phantom regime, where the equation of state is less than -1, meaning the pressure is less than minus the energy density. And the phantom regime is physically quite unsettling. It's associated with all sorts of instabilities and uncertainties about whether things can be quantized. Also, if you make a transition between a phantom regime and a non-phantom regime, you run into modeling difficulties in discussing cosmological perturbations. But for all of these, the phantom regime is something which has been of lasting interest, and so it's going to be part of the investigation here. So that's the model, W0 WA. And before going on to show their result, the first curiosity, which I want you to bear in mind, is that the first thing they do is fit a model with a constant equation of state to the data. So constant W, so this is now just a one-parameter model, and you might call it W0. And what they find when they do that, combining all the data together, is they always find results consistent with W equals -1 and with a very small uncertainty. So you see here for one particular data set combination, 0.997 plus or minus 0.025. So completely consistent with LambdaCDM, and everything they do within this model is absolutely consistent with the LambdaCDM model. And that's the first thing to have at the back of your head. Now, whether that's important or not depends a bit on perspective. It's very hard to make theoretical models, say with scalar fields or modified gravity, that really behave like a constant W model. So they're not thought to be phenomenologically very interesting, but for interpreting the observations, this is a very important fact, we believe. But this is the real stuff. This is straight from their paper, figure 6 of their paper, showing constraints on these two parameters, W0, WA, at 68% and 95% confidence from combining various data sets. So we'll start by looking at the left-hand plot, and the dashed line is DESI alone. And the important point is where the horizontal and vertical lines cross is where the cosmological constant lies. And the first thing to notice is that the DESI BAO data does not rule out that model. It lies somewhere between 1 and 2 sigma as compared to the dashed lines. There's a bit of sociology going on here, really, that when people say DESI has shown such and such, it's actually not the DESI data that shows it on its own. The DESI data is not particularly powerful. It's in combination with other data sets that you get an interesting result. And it happens that the DESI collaboration have brought this new data to the table and done a joint analysis. But in another universe, it could easily have been someone else who came along last and brought their data to the table and did the analysis. And then it would have been called as something else data. So just to bear in mind that the strong conclusions come from merging different data sets together. The left-hand panel shows various combinations of DESI with one other data set, either Planck at the top or any one of 3 possible supernova data sets which are floating around in the literature. But the important plot is not even to have 2 of these together. You get an interesting result only when you bring in all 3 data sets together. And that's the plot on the right, which many of you will have seen as the kind of headline result from DESI. And what you're supposed to notice immediately is that the cosmological constant model, where again, horizontal and vertical lines are intersecting, is outside the 95% confidence limits of these data sets. And I think particularly, it's not so far out for the blue data set, which is the Pantheon Plus compilation, a bit further from the Union 3 and Dark Energy Survey Year 5 compilations. Union 3 more or less includes Pantheon Plus some other things, whereas DES Year 5 is a slightly different sample, but there's enough overlaps that they cannot be all brought together separately. You have to decide which one of them to use. And so all 3 are presented in all of the results. So this is the headline result, and something like 2 or 3, or maybe getting close even to 4 sigmas worth of deviation. So the question is, should we believe that? And the first point I want to stress is that that plot is a little bit misleading because it ignores, or well, that plot ignores a reparameterization invariance of the model. They do discuss it in their paper. It's not that they're unaware of it, but that particular plot doesn't use it. And that invariance is that you can specify any scale, meaning any redshift, at which to specify the amplitude of the equation of state. So you've just got a linear line, and the W naught WA parameterization specifies the amplitude at the present day and a slope. But the data isn't at the present day. The data is mostly around redshifts 0.3 or 0.4, roughly on average. And if you instead specify the amplitude at that kind of redshift and vary the slope around that, you get a much more accurate determination of the amplitude at the pivot scale. And in fact, there's a particular scale you can choose which decorrelates the estimates of the amplitude and the slope. This is called the pivot scale, and the Dark Energy Task Force made this a very popular thing to use. They used it as part of their definition of the figure of merit that measures how accurate different experiments are. The interpretation for us is that the pivot scale is really telling us where the equation of state is best constrained by the data. Their models run all the way from redshift 0 to redshift 1, but the data is really somewhere in between the two. The scale factors that correspond to the center of the data sets are about 0.79 for 2 of the supernova choices, and a little bit higher redshift at scale factor 0.75 for Union 3. So in this pivot parameterization, the constraint on the pivot scale is essentially the same as the constraint that you would get in a constant W model because of the decorrelation property. So because I've already told you that the equation of state W had a constraint very close to -1 with the small error bar, we can immediately conclude that the constraint on the amplitude of the equation of state, where the observations are, is going to be extremely close to -1. And I'll come back to that in a minute. So here's the plot again, their plot from their paper. I'm going to overlay some lines to give us some orientation as to what this might mean. So there's going to be 4 lines, but we're going to start with, there's a red line, vertical line on the left, and a magenta line slightly sloped along the top. And what these lines divide the plane into is regions depending on whether the model has this phantom property, W less than -1 or not. And it can either be never phantom, so W is always greater than -1, which is up in the top right. A model could be always in the phantom regime, the W is always less than -1 in the bottom left, or it can make a transition between the 2 regimes. And the bigger area, the one where the actual data is on the bottom right, are all models which start in the phantom regime with W much less than -1, and W grows and crosses into being greater than -1 by the present day. Now, on top of that, now that's one feature. So the first thing you notice when you look at this plot, going back to here, the first thing you're supposed to notice is that LambdaCDM is outside the best fit curves. But the other thing you might notice if you look at it is this slightly surprising thing that the contours are all very elongated, and you notice they all point very accurately in the direction of LambdaCDM. You take the long axis of any of them, follow the line along, and it pretty much hits the LambdaCDM point. Now, what does that mean? Well, what that means is that at the pivot scale for these particular data sets, the equation of state was equal to -1. And in particular, in this plot, I can draw a line that shows where are the models that have a property of having equation of state exactly equal to -1 at a particular redshift. Now, the blue and the green data, their pivot scale is a redshift of 0.26, and the corresponding line is the blue line. For the union data set, it's the orange line at slightly higher redshift. But what I want you to notice is that these lines go pretty much directly through the data sets. So the data sets are extremely consistent with having equation of state equal to -1 at the redshift where the data is the strongest. And this is an unexpected thing, as is the fact that the data are all lying in the phantom regime. So we've got two surprising things to think about when we look at these results and think about what they might mean. Now, I can show you this coincidence of W equals -1 in another way. Here are the best fit models for each of those three data sets. You can just focus on one of them if you like, or you can look at all three to get an idea of the spread. The best fit model to the data, say the orange one, starts off near the Big Bang at almost -2 for the equation of state. And it grows right through cosmic history, crosses -1, and then continues to increase up to the present, where its value is close to -0.65 by the looks of it. But there's no data way over on the left of this plot, and there's no data way over on the right of this plot. The data is all more or less at this pivot scale of 0.75 or 0.79, depending on the data sets. And we've put dots on the curves of the points where the data actually is. And what I hope you notice is that the points are extremely close to the cosmological constant value, W equals -1. So even though the models spend most of their time away from -1, at the place where the data actually is, they're extremely close to -1. Now, this is essentially a new coincidence. There's various coincidences associated with dark energy already. There's the cosmological constant problem that the value is so small, but there's also the why now problem of why the cosmological constant has just come to dominate the universe in the very recent past, actually around about this sort of redshift. Another way to express it, we've called this the phantom crossing coincidence, this in the data. Another way to express the coincidence, which might be more worrying or interesting for you, is to realize that W equals -1 is the time when the dark energy density stops increasing and starts decreasing. So if we plotted not the equation of state, but the actual energy density of the dark energy, it would be increasing all the way up to the pivot scale, and then has a peak and starts decreasing again. And so the coincidence is that the dark energy's highest value ever throughout the entire cosmic history happens to have taken place in exactly the location where these observations are. And that seems a little bit suspicious. So I don't have much time, so I'm going to skip this point, I think, and just draw to the conclusion. First of all, to reiterate, DESI have a fantastic data set. The amount of work that's been done to reduce that data set and get it into a form where everyone can use it is really quite extraordinary, and people will be using it for a long time to come in its later refinements. But it has this property that's a bit unexpected in two ways. That the best fit models are phantom for most of the evolution, which is very hard to model physically, and that they cross from the phantom to non-phantom regimes within the narrow redshift window probed by observations. Now, a consequence of these features is that while you can find quite a lot of people cheering on DESI because they rule out LambdaCDM, and many people would like to see LambdaCDM ruled out, it's quite hard to find people who are cheering because this actually supports their model, because it's extremely hard to make physical models that live in this part of the plane. Actually, I think maybe I will go back to the previous slide just to stress this point. This is in fact the full DESI prior shown here, again divided into the never phantom regimes and different different regions. And this, I put it there just to show, in fact, when they plot their constraints, they plot only a small region of their prior distribution, which lives here, and they don't show the rest because the plot would be too hard to read. But this is how we'd actually look if they plotted the full prior range. Most of their prior is in models which are phantom. And one of the comments we would like to make is to say that if you just look at the literature of dark energy models before data sets like this came along, almost none of them are phantom models, because these are really hard to make and to make physically consistent. So if you took a poll of where evolving dark energy ought to be, most people would say that it should be in this never phantom quadrant above the magenta line towards the upper right, which is not where the data has appeared. And that's what I mean by saying it's not so easy to find people cheering because they think their own type of model has received strong support from this data. It's only that LambdaCDM doesn't look so good. There's a little caveat to that I will mention since it's here, which was there's a nice paper last week by Schlivko and Steinhardt, who make the point that actually observations are not directly constraining the equation of states. They constrain really the Hubble parameters, a function of redshift, which comes from integrals of the equation of state. And this gives rise to certain degeneracies, and they point out that some quintessence models, which you would have thought lived in the never phantom regime because they always have W greater than -1, nevertheless can quite accurately mimic the models which are near where the observational contours lie in this plot. So they're sort of saying that the W0 WA representation is not necessarily a very good representation of the quintessence model, and it fails in a way that makes the quintessence model look as if it's in the phantom regime when it's not. And that's quite an interesting point, which needs to be worked out in more detail. But back to my conclusions here. So what we feel is that these uncomfortable features may be related to each other, and that the DESI prior seems to be a bit excessively weighted towards the phantom models. Now, their conclusion is somewhat marginal anyway. In 3 sigma sounds good, but 3 sigma for cosmology, we see a lot of 3 sigma type of results, and they don't always sustain into the future. Part of it is helped by the fact that their prior has so much weight in the region where the data has finished up. If you used a more physically motivated prior, that would downweight the phantom regime quite substantially. And that would have 2 effects. One is that it would significantly mitigate this coincidence, this worrying phantom crossing coincidence that we're referring to. But at the same time, it would lower the significance of the entire evolution detection as well. And so the overall take-home message from our analysis, I think, is to say that there is a prior dependence on the analysis. What you get out depends significantly on what you put in as your model assumption, and that analysis that they've done does not really fully characterize the range of uncertainty that might arise when you consider the possible properties of physical models. That's almost the end, but this also has a stop press because last week, on the middle of last week, the DESI team released a new analysis paper doing something a little bit different to try and support the conclusions of their paper of a month ago. So it's a similar analysis, but instead of using W0 WA, they model the equation of state as a function of redshift by expanding it in Chebyshev polynomials. They use 4 polynomials, and so they're able to model more general variations of WA, still in the phenomenological way. And they draw a pretty similar looking conclusion in words that they hint, and I think later in the paper is a clear hint in the conclusions as the language used, that there is evolving emerging dark energy where it's growing rapidly at redshift greater than 1 and then falling. Now, is that really true? This is an excerpt from one of the figures of their paper. I just want you to look at it as a kind of going away message. So the top row is the more interesting one that shows the equation of state. Here's a function of redshift. So the present day is now over on the left rather than the right, as in the plots I showed earlier. And in this case, this is a strange inversion of the conclusion that they saw before. And when they plot DESI alone, which is the gray plot on the left, they see this quite strong evolution. You see the phantom crossing where it crosses W-1. You can see that's where the data are strongest because it all pinches together at that point. If you look at the corresponding dark energy density, which is the plot below, it even goes off the top. This is a sharp peak in the dark energy density, which occurs at the same redshift and then falls off, and it looks really quite weird. Here, the strange thing is that when you add in more data sets, the conclusion becomes weaker rather than stronger. So DESI alone is showing a strong effect. But when you add the Union 3 supernova to get this kind of sand beige colored one, the conclusion is much less strong. When you add Planck as well, so you have the 3 data sets again, it's all becoming much flatter again towards W equals -1. So it seems to me that if anything, the conclusion for evolving dark energy looks a little bit weaker in this new paper than it did in the original paper. It's still there, and they can call it a hint or a clear hint as they wish, but it doesn't look as strong to me in this analysis as it appears to look in the original paper. And that's me done. I think I probably expired my time quite effectively. Sorry about taking a little bit longer than I was intending. But thanks very much for listening.
Questions?
Hi, Andrew. This is Lloyd Knox.
Hi, Lloyd. How are you doing?
Nice to hear from you. And you know, your question raises the question. Well, I'm curious to know what would be a, you know, what's a better prior?
That's a very interesting question, and I'd like to think more about it. I mean, the ideal in all these experiments is that you define a prior based on some physical understanding that came along before you had any data to really tell you what's going on. And for dark energy, to some extent, that's possible because there was a lot of modeling done in the late 1990s, the early 2000s, which very heavily populated the non-phantom part of the plane and only weakly populated the other part. And it would be a tricky but not impossible exercise to try and chart out where models live. A first step in that is done in this Schlivko-Steinhardt paper, where they try to map quintessence models into the W0 WA plane and claim that they can extend down towards where the observational constraints are. So their quintessence prior would be mostly in the traditional quintessence part of the plot, but might have some extension down towards where the observations are, but not into the extreme left-hand edge of the plot. There's also a nice paper by Taka and Takada, which came out almost immediately after DESI. They were super fast, which also have a strategy for mapping quintessence models to the W0 WA plane, which I haven't understood so well. It seems to be at least marginally in contradiction with what Schlivko and Steinhardt are saying, but I haven't got to the root of what's exactly causing that difference at the moment. But that would be one strategy. The other thing to question, I think, is the uniform priors imposed across this enormous, vast prior space, which is being used in the analysis. Where a lot of these models are essentially all heavily degenerate with each other because the dark energy appears very suddenly in the late epochs of the universe. So that's not necessarily a bad thing to say the models are all observationally indistinguishable from each other, but the prior does seem to contain a lot of models of that kind. Mm-hmm. The alternative is, it's, you know, in my view and Marina's view, I think it's not to say that one prior is right or wrong. We are only advocating that people should always remember what the priors are. And when you have a result which is maybe 3 sigma, it's likely to carry quite significant prior dependence. And it's nice to try and estimate that in some way or another to try and understand how big a difference you could get if you chose a different prior. If the data gets much better, if someone comes along with a 7 sigma result, then it doesn't really matter what you thought the prior was, because the data is going to overrule any amount of cleverness or stupidity you might have made in your prior choice. But in the regime we're in just now, there's definitely room for thinking about it more, and also just trying to use our physical intuition to guide us as to whether or not the result is absolutely as strong as is being claimed, or is maybe a little bit weaker than is being claimed.
Yeah.
Could I ask a question about slide 22? Can you go back to slide 22?
This one, can you still see it?
Yeah, yeah. So from this, it looks like, if I'm that, you know, all you're saying that these experiments are all doing their measurements in the same regime of A, right? That's one, okay, and they're
this is kind of the central point, if you like. It's so they have an extent in scale factor, but that's the
but
statistical
to
way
some first order approximation, they're clustered very close in A, and so I think I can. Is it correct? I can think about this as they're sort of measuring at that point. They're sort of measuring W and its slope. In other words, they're sort of measuring the evolution in that window, right?
Yes, that's right.
Yeah, and then and of course you can see from this that, you know, because you're extrapolating over quite a large range, right? So the exact model, the fact that you're, for example, extrapolating with a straight line is pretty important here, right? That was, I guess, the point of the Chebyshev polynomials, is to try something more general, right?
Yes, which is a good idea. There's various, you can use bins, you can use Chebyshev polynomials, you can use Gaussian process. With these, you get a sense of what the actual range of constraining data is by looking to see how pinched the data become. You can, on some scales, the W is much more accurately determined than on others.
It seems like it would be much less misleading if the results were quoted as, you know, basically some parameters that basically tell you the value of W and its slope at that place, right? I mean, that would have been something that models could try to fit and so on, but extrapolating it, it just seems like extrapolating it to zero and reporting it in this way is unnecessarily confusing. Maybe, I mean, I'm just an outsider, but to me, that seems like, why would you do that?
Yeah, I think it's a historical thing that people have done that, but I agree absolutely. I mean, they're completely aware that there's a pivot scale.
It comes from the funding stage.
Okay.
Right, because
maybe people agreed on some benchmarks when they thought there was no signal, but okay, now that there's apparently a signal, maybe that was not the right benchmark or something. I don't, but I mean, it just seems like that is the measurement, and then
it's not just the measurement though, because you're combining these things, and there's also this integral constraint from today to last scatter.
Okay, so you're saying it's not correct that all the constraints are clustered there. There are constraints that effectively integrate over a larger range.
Yes.
Okay, so okay.
And when you ask where is it best constrained, that, you know, for these data set combinations, it's there.
It is,
but
it's dominated by there, but
it's not.
still...
That's where, if you ask where is it best constrained, it'll give you an answer in one place, but that doesn't mean that's where all the information is.
Yeah, so you're saying, your prior has to specify the whole range. In other words, you have to give a model, your model or whatever you're setting to has to specify the whole range.
Absolutely.
Okay, I got it. Thanks. That's
so this kind of plot gives a better sense of that, I think.
Yeah,
I see. Thanks.
I mean,
I guess ideally
won't these data always be best constrained at a redshift of 0.2, 0.3, 0.4? Like, there's no getting away from that, is there?
Well,
what I guess I mean to say is it an important statement that the data is best constrained there if that's always going to be true. Really, what Lloyd said is it's like the width of the constraint, right? Not just where it is best constrained.
Yeah, there's the strength of the constraint. You can also, you could try to push some of the observations out to higher redshift. So I think the baryon acoustic oscillation data from DESI does extend all the way out to redshift 2, but it's not actually very usefully constraining there because all of the models that they're discussing have negligible dark energy at redshifts of much above redshift 1, and so no amount of fantastic data at those redshifts is going to help you if you're in that regime. And that's very important to always to remember that in any redshift region where the dark energy density is predicted to be negligible, the equation of state can do absolutely anything and you have no sensitivity at all to it.
Sorry, I just ask again, your sort of your original point, I mean, ideally you may want to say, you would want to say, I just want to see the data is ruling out LambdaCDM. Okay, just some statement like that. But you're saying that the current data actually fits it quite well. Is that the right statement? You said that they get W-1 with small error bars. Is there, I mean, would that be a more robust way to try and say that something is wrong, as you just try to say that the LambdaCDM is a bad fit with DESI and everything else?
If you're a proper Bayesian, which I like to be, you only compare things with other things. You don't just rule out one thing versus another. So here there's a definite comparison going on between LambdaCDM and the W0 WA model, which has the capacity to rule out LambdaCDM. It will, however, be odd. It's going to rule it out in a direction where the equation of state itself is consistent with -1, but its slope is substantially different from 0, which sounds a priori a bit odd. I see Marina's raised her hands. Maybe I'll let her comment further on this.
Oh, actually, I forgot what I was going to say.
Oh. Okay.
God, it'll come to me.
Sorry about that.
Oh,
Emily.
no, I do know. Sorry. Well, because you guys are theorists, I guess, it's quite important to bear in mind that this is DESI starts at DOE. It's a DOE-led experiment. And if we still need, from the theory side, we will always need a very good verification experimentally to convince us that LambdaCDM is still up and running as theorists. If we look at over the entire pipeline of from the theory insertion all the way to the data analysis, and so even if this is a null result, which I believe most in the community believe that it will not live up to, they are waiting for the year 3 DESI data, which will confirm or deny. But it's also important to know that the best team in the world is measuring a result that might be null. And in theory, well, in funding discussions, it's sometimes very difficult to fund an experiment that just to confirm that LambdaCDM is there. But we in the theory side need very good confirmation that we really need to work that much harder to implement deep into the foundations of theoretical physics, this LambdaCDM that nobody can do anything with in cosmology. And you guys are then next working on this. Thanks.
Okay.
No further questions?
Well,
Oh,
I was just saying one other thing, which is that Andrew, just to your first half of the talk, I appreciated your point, and it's been a interesting thing that, you know, these models to reduce the Hubble tension generally don't provide a better fit to Planck. You know, the CMB data.
Yeah.
Yeah. In fact, in Francis Jan's here, we even explicitly constructed something that would not change the CMB fit.
Right, but you have to be quite careful in how you do that. Right. Nature is not choosing its models based on trying to trick us into thinking it's LambdaCDM when it's not.
Right. I mean, at one point we had this tension between low L and high L in the Planck data on the value of the matter density. And I was hopeful that was actually connected to this problem, but that didn't persist with adding in better data and better temperature data and polarization.
Yeah.
all right. Let's thank Andrew again.
Okay. Thanks for the invite.